Hello and welcome to this session. In this video, we will focus on learning outcome 2, understanding the factors that affect the rate of a chemical reaction. Chemical reactions do not all occur at the same speed. Some are rapid, while others are very slow. This session explores what determines how fast reactants are converted into products and introduces the key factors that influence reaction rates. By the end, you will have a clear understanding of why reaction speeds vary and how they can be controlled. The rate of a chemical reaction is how quickly reactants turn into products. It's measured by the change in concentration over time. Reaction rate hinges on particle collisions. Successful collisions depend on energy and orientation. The collision theory provides the foundation for understanding these dynamics. Increasing temperature boosts particle kinetic energy. This leads to more frequent and energetic collisions. More particles have energy equal to or greater than the activation energy. Consequently, the reaction rate increases significantly. Lower temperatures have the opposite effect. Higher concentration or pressure means more particles per unit volume. This results in increased collision frequency. According to collision theory, more collisions lead to a faster reaction rate. Lower concentrations slow down reactions. The same principles apply to gases under pressure. Increased surface area exposes more particles to collisions. This leads to more frequent successful collisions. Powders react faster than larger lumps due to this principle. Collision theory explains how surface area boosts reaction rates. More exposed particles mean a quicker reaction. Catalysts speed up reactions without being consumed. They provide an alternative pathway with lower activation energy. This increases the proportion of particles with enough energy to react. Collision theory shows how catalysts enhance reaction rates. They don't alter the energy change of the reaction. The nature of reactants influences reaction speed. Ionic reactions are typically faster due to easier bond breaking. Weaker bonds require less energy to overcome. Aqueous reactions often proceed more quickly than solid-state reactions. Collision theory supports these observations. Lower activation energy results in more successful collisions. Higher activation energy slows down reactions. Catalysts work by lowering activation energy, not increasing energy. The rate depends on collision frequency and energy. Key factors include temperature, concentration, and catalysts. Collision theory explains reaction rates through particle interactions. Particles must collide with sufficient energy and correct orientation. Successful collisions per second determine reaction speed. Temperature and concentration affect these collisions. Catalysts lower the energy barrier for reactions. The Maxwell-Boltzmann distribution shows particle energy spread. The x-axis represents kinetic energy, while the y-axis shows particle count. The area under the curve remains constant. Temperature shifts the curve, affecting reaction rates. More particles gain energy to surpass activation energy. At lower temperatures, the curve is taller and narrower. Fewer particles have energy to overcome activation energy. Higher temperatures flatten and broaden the curve. More particles exceed activation energy. Reaction rates increase as temperature rises. Activation energy is a vertical line on the graph. Only particles with energy above this line can react. Temperature changes increase the fraction of particles overcoming activation energy. Even small temperature increases boost reaction rates. Collision theory and the graph explain this relationship. Higher temperatures mean higher average kinetic energy. More particles exceed activation energy, leading to faster reactions. Successful collisions per second increase. The Maxwell-Boltzmann curve and collision theory explain this. Reaction rates are directly linked to particle energy and collisions. The area under the curve remains constant as temperature rises. The curve flattens and shifts right with increased temperature. More particles have energy to overcome activation energy. Activation energy itself remains unchanged. These points are crucial for understanding reaction dynamics. Increasing temperature raises reaction rates. The Maxwell-Boltzmann distribution shows more particles with enough energy. This energy surpasses activation energy. Collision theory and energy distribution curves explain the phenomenon. Temperature is a key factor in chemical kinetics. Temperature, concentration, and surface area affect reaction rates. Catalysts provide alternative pathways with lower activation energy. The nature of reactants also plays a role. Collision theory underpins these factors. Understanding these elements helps predict reaction speeds. Understanding reaction rates is crucial in industrial processes. It influences product yield and efficiency. Adjusting temperature and concentration can optimize reactions. Catalysts are vital in many chemical industries. Knowledge of these principles aids in process design. Catalytic converters in cars speed up exhaust reactions. Enzymes in the body act as biological catalysts. Industrial ammonia production relies on optimized reaction conditions. Temperature and pressure adjustments are common in chemical manufacturing. These examples highlight the importance of reaction rate control. Reaction mechanisms explain step-by-step processes. They reveal intermediate stages and energy changes. Understanding mechanisms helps in designing efficient reactions. Collision theory and activation energy are key components. Detailed study aids in predicting reaction outcomes. Advanced study delves into reaction dynamics. It explores energy profiles and transition states. Computational chemistry aids in modeling reactions. Understanding these concepts enhances chemical innovation. They are crucial for developing new materials and drugs. Research continues to uncover new reaction pathways. Sustainable chemistry focuses on efficient processes. Novel catalysts are being developed for greener reactions. Understanding reaction rates is vital for future advancements. The field is evolving with technological progress. In conclusion, this video has examined the factors influencing chemical reaction rates, from the principles of collision theory to their practical applications. A thorough understanding of these concepts is essential for optimizing reactions and contributes significantly to the advancement of chemical science. For any queries, send us a WhatsApp message at 07484361688 and a team member will be happy to help. Thank you, and we look forward to the next session.